Welcome, everyone. This is session number 4 of 8 of the webinars we're holding this year to help math leaders across the state develop and refine their math intervention structures within their culturally responsive multi-level systems of support. I'm Heidi Erstad, a technical assistance coordinator from the Wisconsin RTI Center, and I'll be facilitating today's session. I'm joined by my colleague Sarah Sum, who led us in the first and the third sessions, and will be working behind the scenes today to answer questions in the chat box as they come up. Ken Davis, the math consultant from DPI, can't be with us today, but we'll be hearing from him later through the magic of technology. We're also going to be joined by 2 guest speakers from Cudahy, and we'll introduce them when we get to their section of the webinar. This webinar is being recorded and will be made available on the RTI Center YouTube channel and the website, along with all of the presentations and resources shared today. We will email you the link by tomorrow, letting you know that they've been posted along with all the materials. Each topic in our series comes from the recommendations in the Institute for Educational Sciences Practice Guide for assisting students struggling with mathematics. In previous webinars, we've discussed the role of screening, motivational strategies, and intervention content. These next 2 webinars in January and February will feature powerful instructional practices. Today's webinar focuses on the use of visual representations as an important instructional strategy when delivering interventions. Next month, we'll talk about systematically planning intervention instruction. Our agenda today will follow this format. We're going to spend about 10 minutes looking at the research to ground us in some theory and some results. And then we're going to have about 45 minutes to hear from practitioners on what this looks like in action in Wisconsin schools. We're going to spend about 5 minutes for reflection and resources. And then because we have so many participants online at once, we're going to ask that you use the chat box to ask questions throughout the webinar as they come up. And we'll also have time at the end for Q&A and stay on after the presentations are complete until about 10:15 to address questions or chat further. There's 2 parts to today's featured practice. The first part in yellow tells us that we need to make sure that students participating in interventions have substantial opportunities to work with visual representations of mathematical ideas. The second part of this recommendation in orange is just as critical. That is, we need to make sure that those delivering interventions know how to systematically use visual representations to develop student conceptual understanding and fluency with numbers and concepts. I do want to point out that this connects too with the NCTM principles to actions. Using and connecting mathematical representations is one of 8 identified high leverage practices that NCTM suggests for improving student level learning at all levels of support, not just for interventions. I also want to connect this back to last month's webinar on that was focused on the content of interventions. We learned that intervention should focus primarily on student understanding of and operations with whole numbers and rational numbers. So today we'll be focusing on the use of visual representation in these domains. So let's start today by looking at what the research says about the role and effectiveness of visual representations in student understanding. And then we're going to turn it over to our guest speakers to talk about some practical ideas and examples in action. According to the research cited in the IES practice guide, students who struggle with math essentially struggle with connections. Not understanding the relationship between visual representations and mathematical symbols and notations is a problem. According to the National Research Council, representations provide us with our gateway to understanding abstract mathematical ideas. So here's an illustration. For those of you who were here at the start of the webinar, I asked you to solve that problem 18 times 5 in your head. I want you to think back to that problem. If you think about students who have a weak foundation in fluency with number, they can only solve that problem in their head by using an algorithm like the one you see on the screen, perhaps writing that problem in the air on an imaginary piece of paper. According to the National Research Council, these students have learned that for each kind of math situations, there's really only one correct procedure. And with that thinking, the seeds of disconnection between their own reasoning and strategy development in doing math are sown. They say that the problem isn't that students fail to solve the problem accurately using a procedural approach. In fact, they may be more accurate. But when the nature of the problem changes, or the numbers change or get bigger, or contain fractions and decimals, or students haven't had a procedure for a while or practiced it, students may feel completely lost when confronting a new problem, or simply even gauging whether the result makes sense. But if instead we want students to be algebra ready, we need them to be willing to break apart numbers and regroup them. Algebra ready students need to be able to think quantitatively, abstractly, flexibly, and fluently. And that takes a different type of instructional approach. Stanford education professor Jo Boaler talks quite a bit on her UCubed site about how visual representations and number talks combined can build on students' natural understanding of numbers to more sophisticated levels. To illustrate that, here's what she did. She asked Stanford students the same 18 times 5 question as each of us solved earlier, and then made the visual representation of each student's solution. Here's a sampling of some of the students' results. So Neil, for instance, took 18 and halved it, and then multiplied 9 times 5 and 9 times 5. Ricardo made the problem into 9 times 10 because it's the same. Sammy broke the problem into 10 times 5 plus 8 plus times 5. Jamie solved 20 times 5 and then subtracted 2 5s, and so forth. According to Dr. Boaler, each of these visuals highlights the mathematics inside the problem and helps students develop understanding of multiplication. Pictures can help us see how ideas and mathematical notation connect. In this instance, we can see how associative and distributive properties of multiplication work, and that aids in our understanding. This doesn't mean that all of these strategies are equally good, but if students can see that for each kind of math situation there can be several correct methods, their engagement in their own strategy development is kept alive. As shown through this example and supported by a range of research, the use of visual representations in instruction has multiple benefits for kids learning math. First, visual representations can provide students with ways to access abstract ideas. While this is certainly good for all learners, it's particularly useful as a universal design for learning strategy for students with learning disabilities or for whom English is a second language. If a student cannot read or understand spoken English, visual representations help students immensely in learning the content presented to them. Visual representations also provide students a concrete way to work with abstract math. For example, the mobile in the corner from the free online Solve Me puzzles shows at a glance how visual representations can help students make sense of using variables and balancing equations, foundational work for algebra. And kids can draw on these visual representations when they're working to understand a concept or problem. Visual representations can help support students communicate their mathematical reasoning, an important standard of mathematical practice. This communication also provides teachers with a window into student thinking and helps peer discourse as well. And when multiple representations are used, such as visual with verbal, student learning is deepened. Transfer of learning is more likely too because students are asked to make those connections within and between concepts. But I want us to keep in mind that this practice guide recommendation goes beyond just using more visual representations. It also asks us to think about which visuals are the most effective forms. We need to try to keep in mind that certain visual representations are better suited for certain types of problems and for understanding. Here's an example from the resource Making Sense of Algebra. On the bottom part of the screen, you can see two visual representations that both illustrate that 4 times 3 is the same as 3 times 4. But the cookies on the plate model not only hides a key property of the operation of multiplication, it's also a bit mystifying and will likely leave kids asking where that extra plate came from. The cookie sheet, on the other hand, is an array that models the standard multiplication algorithm and is generalizable. So it's a better visual representation for focusing kids' attention on the essential properties of multiplication. In the panel's opinion, teachers are better off consistently teaching students to use a few types of visual representations rather than overwhelming them with many. Number lines, arrays, and strip diagrams are highlighted in the guide as being particularly useful in helping students to focus in on what's critical in the math ideas they're seeking to understand. The practice guide contains many examples of these tools in action. At the bottom of the right of the screen, you see one of those examples. This one illustrates how a strip diagram can help students make sense of a problem with fractions. And our guest presenters will be sharing other high leverage examples. The final piece to this puzzle that we want to highlight from the practice guide is shown on the screen about the way that visual representations are used. Note that we've highlighted some key ideas here that will severely limit the effectiveness of using visual representations that make gains with students. If we use visual representation as a series of unconnected activities or in a scattershot way, we'll be compounding students' misconceptions rather than building on their understanding. So we want to think about not just using visual representations or the right ones, but using them in a scaffolded way. According to the National Research Council, by the time students begin algebra, they need to have a rock-solid network of understanding of the number system. Students can then build on that knowledge network to support new algebraic understanding. To build up that foundational knowledge network, we need to make careful choices in planning interventions that guide students through a coherent learning path. We need to scaffold and build learning pathways from the concrete to the representational to the abstract, connecting students' background knowledge, real-world experiences, and intuitive number sense to a more sophisticated and precise learning. Through planned progression, students learn both the how and the why to the problem-solving procedures they use, and they learn the what. That is, they develop conceptual understanding of the math concepts that underlie the problem-solving process. There are many sources of instructional progression frameworks. The one we see on the screen is the concrete representational abstract instructional model. The IES practice guide gives us more examples of how to structure these progressions, and our guest presenters will be sharing the frameworks they use. We're also going to share some resources at the end of the webinar so that you have access to those. You'll note that most of these instructional progressions start with the concrete and build from there. The authors of the practice guide support the use of manipulatives at the initial stages of understanding. They do caution, however, that students manipulating only concrete models may not be learning to think abstractly. So you'll want to move into the visual as soon as possible to connect thinking with representations. And finally, we want to finish up this research section by noting that there are a number of outcome studies that strongly support the use of visual representations to achieve positive learning outcomes for students. We'll provide you with links to these. We'll provide you with links to these studies and others on our resource document that we'll share with you. So at this time, I want to turn it over to our guest presenters. We're really excited to have some practitioners here to talk about what visual representations look like in practice. I want to introduce Jamie Neary and Dina Mendola. Jamie and Dina worked together in Cudahy, and now Dina is also working for the Math Recovery Council. So I'm going to turn this over to them.
Thank you and welcome. My name is Dina Mendola. I am currently an instructional coach with Math Recovery. Prior to that, I have worked with the Cudahy School District for 16 years. And within our school district at that time, we were partnershiped with UW-Milwaukee and Core Mathematics Project. And my coworker here is?
I'm Jamie Neary, and I currently still work in the school district of Cudahy as a third grade teacher, and I have a focus in math. I was a part of the partnership with UW-Milwaukee in the core program, and then I also am AVMR 1 and 2 certified.
So our learning intentions for today is that we are learning how to deepen our students' fluency and understanding of mathematical content through the effective use of visual representations. By the end of this webinar, we know that we're going to be successful if you are able to walk away and use visual models to support the development of fluency and conceptual understanding. If you're also able to scaffold instruction to push students towards their cutting edge of knowledge, as well as overcome obstacles that manipulatives and pictorial representations may present. And finally, support student learning through the use of powerful instructional techniques.
Dina?
So I want to begin with,
I'm going to interrupt you for a second because we don't see your screen.
Okay. Do you see it now?
Yep. Thank you.
Oh, no problem. Okay. So going back, I'm going to talk about some common misconceptions that we often see during intervention. There are two extremities with this, and one is that if I focus my students' learning on mastering their facts and their computation, the understanding will follow. And this is usually where we see the skill and drill and the flashcards and items like that to try to build that. And the other side or aspect of it is that if I focus on using manipulatives, students will make connections to the skills and apply it to the algorithm. But the goal is actually, there we go. All right, the goal is actually to emphasize the learning with both a solid understanding and application of the mathematics. The shocking realization is that problem solving and mathematical thinking skills can become quite limited without intentional and direct instructions. So students must know the why behind the procedures and the use of manipulatives as well as how they work. Teaching must be intentional to promote this strong mathematical thinking and emphasize the learning. So with academic interventions, students that are not successful in the universal curriculum need further instruction targeting each of the students' foundational understanding. In order to make these academic growths, instruction is provided in addition to the core instruction. It must use strategies based on students' cognitive learning styles. And finally, it must effectively build upon previous knowledge and understanding. In order to reach all learners, it's important to scaffold instruction with the use of these visual representations. So below you see the concrete, the pictorial, and the abstract model. But we need to be aware that concepts are best mastered when they are presented in an intentional developmental instructional sequence to support and build upon these connections. It's important to be both direct and systematic with our instruction so that we can meet the needs of our students and see significant academic growth. So we must first begin with concrete instruction, where the students are able to move and manipulate different mathematical tools to help build that foundational understanding. Once that understanding of the concept is developed through the use of concrete, we need to begin to phase into pictorial. Pictorial includes drawings, diagrams, charts, or graphs that students can relate back to those concrete objects and to the conceptual understanding. Lastly, students will need to transition into thinking abstractly. Let me just move this. Abstract thinking includes a symbolic representation such as numbers, letters, and the standard algorithm. Here's an example of why this progression is important. I want you to take a moment and think about how would a student answer this question? Which is larger, 1/3 or 1/6? Many of our students would say that since the 6 is the larger number, therefore 1/6 is bigger than 1/3. That's the reason that instruction with concrete and pictorial is so important. Our students will lose meaning around the quantity and develop misconceptions that become habitual. So here's how we support that understanding around quantity of 1/3 versus 1/6. When we think about how we can apply this progression to fraction questions posed in the previous slide, we would want to begin students with numerous hands-on experience with concrete materials such as fraction strips, fraction bars, and Cuisenaire rods. From there, we would move their thinking into pictorial representations to develop student awareness of the fractional sizes. These representations can include tape diagrams, empty number lines, and such. This ultimately will lead towards abstract thinking and understanding, or the symbolic representations, so that they will actually develop an awareness that 1/3 is larger than 1/6. To develop full mathematical understanding, a teacher must need to incorporate each aspect of the STAR model that is shown here, which is also found in Principles to Action by NCTM. This includes overlapping of the visual, the physical, the contextual, the verbal, and the symbolic. When one or more of these are lacking, students can fall into deficits that create gaps due to the lack of conceptual understanding.
So you might be asking yourself, what does this overlap look like, and how do I implement this to assure deep mathematical understanding of facts and concepts? So here are some overlapping examples. When topics are presented in abstract form from a worksheet or in a textbook, teachers need to provide manipulatives for students to use and then have them represent their drawings pictorially. So we cannot forget about our auditory learners, and we need to make sure that they're explaining their reasoning. This helps them build understanding of quantity and develop relational thinking, which is how numbers relate to one another. So you can see in the example with the bead string, how they're moving beads over and they're connecting the jumps with the numbers, and then additionally connecting it to that abstract thinking with 56 plus 32. So they're taking the little steps. On the right-hand side with the counters, they have the concrete model set up on their desk where they're using the 3 red counters and those 2 yellow counters. They then are transferring it to make a pictorial drawing and then connecting it to the abstract thinking of the numbers 3 plus 2 and how that quantity of 3 plus 2 is 5. Here's some overlapping examples using early understanding of multiplication and division. So in this first example, we're using groups of and empty number lines to show the commutative property. So your concrete understanding would be students using counters and laying them out in an array. The pictorial, to move them to that pictorial understanding, would be using an empty number line where they're showing each jump as a group and then drawing the array and circling what the groups are. Lastly, their abstract thinking is connecting the equations for that first example with the red counters. That's 5 groups of 3 makes that 15, and then the yellow counters, the 3 groups of 5 makes that 15, and then connecting them together, and you would want them to explain that, well, 5 groups of 3 is actually the same value as 3 groups of 5. You can also show it with the distributive property for fact fluency. So you really want to push their thinking to go to a fact that they know. So providing them an array to lay out on their desk with counters would be that concrete model. After that, you would have them pictorial, draw the array out on a piece of paper or a whiteboard, and then you want to show them the chunk that you want them to focus on, that 5 times 3. Lastly, you're going to connect it to that abstract thinking, showing the equation sequence that they did a 5 times 3 or 5 groups of 3, and then they added in that 1 group of 3 to get their complete quantity of 18. Anchor charts are really important to use in the classroom because they can be ongoing support beyond the intervention hour. So it's important that after you talk about things during your intervention hour, you have anchor charts hanging up in your classroom so students can refer to them during that whole group instruction. Here's another progression to the algorithm by extending multiplication understanding with place value. You can see that students were asked to lay out what 12 times 13 would be with place value manipulatives. They then take that and draw it out in an open array, which is on the left side of your screen. They then need to make connections with how they are finding the quantities. So that 36 is that 30 plus 6 that they are adding together, which is only part of that array. Then that 120 is that other part that they didn't include, which is the 120 added together. And then when they put those two amounts together, they get the full quantity of 12 groups of 13 makes that 156. Here's some overlap examples for fractional understanding. You might want to have students start their fractional understanding with concrete fraction strips, where they're able to cut, fold pieces of paper and connect them from one to the other. Then that pictorial drawing is drawing it out using a number line, showing what those quantities represent. Then lastly, the abstract is using that equation. So if you look at the example that says 4 times 5/8, you can see at the bottom they're representing it with their equation. 4 groups of 5/8 makes 28. And it's really important when you have them do an abstract equation that they connect back what each of those numbers represent from the problem. That's really making sure they're understanding the equation and they have a conceptual understanding for what the numbers mean. Hold on,
Okay, so you might be wondering, how does this look during instruction? During the intervention hour, and how can I use this type of progressive mathematization to build solid, strong connections to help your students make academic growth? This video, you're going to see a student working towards building fact fluency by applying their knowledge and their use of that concrete material to make connections. I would like to note that for the privacy of the student, there is a blurred face option being used. So you're going to notice this as a video plays, but please listen carefully to the dialogue and the discussion and how the student instruction is focused on making these progressions. Okay, how can we solve 8 plus 5?
Well, we could put our 8 in our chart with blue. And then we could put 5 with red for our 5. And we can move 2 up to make that a 10. And we would split this up into 2 and 3. And this would make a 10. And then we have 3 left over. So we just move this 3 down. And 3 plus 10 is 13. So 8 plus 5 is 13.
Good. Now what happens if I turn this over and we don't have that anymore? And I'm going to take a new chart. And I want to write 8 plus 7. How can I do that this time without my 10 frame, but to think of what you just did?
Well, we could split this up into 2 and 5 because we know that makes 7. And we could put our 8 and our 2. That would make 10. and we could move our 5 down here, and 10 plus 5 is 15, so 8 plus 7 is 15.
Okay, and what if I would erase that and write 9 plus 4? How would I solve that? Actually, let's even turn the board over. How would I solve 9 plus 4?
Well, we could do 9 and just add 4, 9, 10, 11, 12, 13.
Okay, is there a way that I can do that with my mate 10?
We could split our 4 into 3 and 1.
Okay, show me.
We could split this one into 3 and 1 and group our 9 and our 1 together to make 10. Move our 3 down here. 10 plus 3 is 13. So 9 plus 4 is 13.
Good. Okay, I'm going to hide this one more time. How would I do that with 9 plus 7?
We could split our 7 into 5 and 2. Or we could split it into 6 and 1.
Why would you want to split it into 6 and 1 instead?
Because you could make 9 and 1 as a 10.
Oh, okay. So then what's 9 plus 7?
9 plus 7 would be 16.
16. Because you paired the 1 with the 9?
Mm-hmm.
And then you had how many left over?
6.
So that's the same. 9 and 7 is the same as 10 and
6.
So 9 plus 7 is
16.
Very good. So after watching this video, okay, how can we solve 8 plus 5? I apologize, sorry. After watching this video, what would your next intervention step be to build fact fluency with this student? Some aspects to keep in mind with our past discussion is she already had the concrete, the pictorial, and the symbolic exposure. So where do we go from here? Do we go towards the standard algorithm? This video is going to illustrate the push towards taking that work that we have just done with this student and develop knowledge into building automaticity to fact fluency. Notice the way that the student solves these problems and listen carefully to the required dialogue that's involved in making these progressions. It is very important to make sure that when doing this, the student's verbal explanation connects and supports all that work you have previously done with the concrete and pictorial representations. Nice and loud so the camera can hear.
8 plus 3. If you have 8, you take 2 away from the 3, then it will be 11.
Good.
9 plus 7, if you have a 9, you take 1 away from the 7, then it will be 16. 9 plus 4, you do the same thing for the 4, so then it will be 13. But 10 plus 8 would be just 18.
I want to find a tricky one here. What is she going to do?
Even though you have an 8 plus 7, you could really take 3 away from the 8, but I'd rather take 8 from the 7.
You mean 2 from the 7?
Yeah.
Yeah, you'd rather make the 8 a 10, is that what you're saying? Okay, so what would this be?
16.
16?
15.
15, yeah. I would do the same thing. I think that's easier.
6 plus 7, you take 3 from the 6, and then it will be 14. 13.
13, there you go. So you can see how all that work that we have done finally is translating into building that automaticity with fact fluency. Now, when we're doing all this, and we still seem to feel like there are these obstacles, and we are following these progressions and students are still not making connections, the question becomes, how do we go back and pinpoint where those struggles are at, and how can we alter our instruction to build efficiency and a stronger connection? In the next few slides, we're going to talk about sharing several common misconceptions, instructional flaws, as well as ways to overcome these obstacles that we can help our students build a stronger number sense. First, I want you to remember this warning. Not all visual representations are created equal. The use of manipulatives and representations does not automatically provide a conceptual approach towards building understanding. If there's not a clear connection with the purpose, they too can become just a process and a procedure that is completely void of any meaning. So we're going to go back and analyze how manipulatives and pictorial representations were used. Were they used with strong mental connections or simply as procedures which eventually become a crutch to students? Let us demonstrate. In this example, I want you to think, is there a strong conceptual understanding around place value, or is it a procedure of using sticks and dots? A student lays out 3 sticks and 5 squares and simply indicates that there are 3 10s and 5 1s. Where is the mathematical connection to build conceptual place value? With the previous instruction, the move towards pictorial would be such as this. Oftentimes, we will see students solve these problems with sticks and dots. Here you see a student representing the first quantity by drawing 3 sticks and 5 dots to represent 35. From there, they draw 1 stick and 2 dots to represent the 12. In order to take away the quantity, they're going to take away 1 stick from both of the quantities, and then they will take away 2 dots. When they're done, they will simply count the remaining sticks and dots to get the answer of 23. If you notice this, it resorts back to a count 3 times strategy where they're counting and drawing out the entire first quantity, the entire second quantity, and then they're recounting to find the solution. Also, we must notice that this visual representation does not match the problem. If you're looking at the quantities, once they draw it out, there are not a total of 35 to start with, but rather we have 47 illustrated as our starting. Another deficit with this is students easily lose track of their stick and dot drawings. And finally is the fundamental foundation of incrementing and decrementing by place value present. So you might be asking yourself, how do we move students beyond this? Just as the use of manipulatives does not automatically provide a conceptual approach to build understanding, the same is true with pictorial. On the right, you see a problem solved using a visual representation. However, this student only draws an illustration of the problem or just of a picture of the story. Have you had students illustrate problems like this? The mathematical thinking and the answer gets lost in the details of the drawing. Now, I want you to also look at this number line below. This was a number line that was used for representation of subtraction. The student is moving from left to right, which actually indicates an increase on a number line rather than a decrease that is meant of subtraction. Although they are subtracting correctly, they land on the correct answer. The representation is not accurate. So if we are trying to build a solid understanding, we have to make sure that the mathematical thinking is accurately represented and it matches the problem. For example, in the empty number line, if you're solving a subtraction problem, the largest quantity should be displayed on the right and not the left. Once again, you might be asking, so how do we move students beyond this? Methods to overcome these obstacles is to have instruction be broad and overlapping. We must overlap each of these stages consistently to get at the heart of student learning. After working with concrete materials, students begin drawing representations of the materials they are using. Both are being incorporated at the same time so that students can see the visual connections. This is the overlap. First, let's start with the way that we can overcome these obstacles by bridging the gap from concrete to pictorial. How do we move away from needing concrete items to a clear understanding of pictorial representations that they will be using? In order to overcome this obstacle and bridge the gap, we must distance the setting and not bypass pictorial and go straight from the manipulatives to the abstract. We have to begin slowly moving towards less support in building this understanding. A way we can do this is by screening quantities or partial quantities. We can also further distance the setting by having students create concrete and pictorial representations and remove color, use a larger range of numbers to push thinking forward, and slowly start to move them from that concrete to the pictorial. Once students have moved to those pictorial representations, we still need to have them go back and return to the setting and check their answers with concrete items in order for them to continually make connections and draw upon mental imagery of the quantity. I want you to reflect on your classroom. Do you go straight from the manipulatives to abstract, or is there a transition? Do you revisit the concrete? Do you screen the first quantity or the second quantity? What about the range of numbers that are being used? Remember back to the stick and dot use for place value? Here's a real teaching example of how we can use that distance the setting to build a strong foundational understanding.
7 plus 31 equals mystery box.
Yeah, we don't know, right? So we have to solve that. Show me how you can solve that.
We could do 2 tens, 7 ones, and then plus 7, and then 3 tens, and 1 one.
Okay.
And then you just do 10, 20, 30, 40, 50, 51, 52, 53, 54, 55, 56, 57, 58. Then our answer is 58.
Okay, can you put it in the box? Okay, so I saw you made your first amount, which was how much?
27.
And then you made your second amount, which was?
31.
And then what did you do?
Then I just counted all of them.
You counted all of them up, right?
Mm-hmm.
How many were there in that first amount?
27.
27, yep. Is there a way, if there's 27 there, how could I use what I know is under here? How much is under here again?
27.
How could I use that and this to help me figure out the total? I'm going to cover the total again. I don't know if you remember it. But if I have 27 that I'm starting with, what happens?
Because these are tens, and then the little dots are ones. Then you just do 10, 20, 30, 40.
Okay, but how many are under here?
27.
27. So if I add, remember all this, if I add this one onto it,
it would be 37.
Oh, so there's 27, this would be 37.
Then 47, then 57. If you add the 2 more.
And then what about that?
And then 58.
58. You were doing some thinking there. What were you thinking about?
That there was, if you had 2, then you add 3, then it would be 50. And then if you had one more, and because it was 27, then it would be 58.
So you're splitting your tens and ones.
All right, so now we're going to be focusing on bridging the gap, from pictorial to that abstract thinking. So you might say, how does this look when moving from one to the other? Well, here's the distancing the setting in action with multiplication. So in order to distance the setting from concrete and pictorial to abstract thinking and multiplication, students would draw a full array as shown in the slide. It's that first picture. From there, we would provide partial screening where the start of the rows and columns are still exposed so that students can use these markers as a visual representation of the covered quantity. To push thinking more abstractly, we only expose students visually to a single row, yet we want to make sure that our wording is clear and we're stating that there are 6 rows of 5 dots. Finally, one would just show the equation and students can draw from those mental images which were established by this transition. Now, it's important to note that many curriculums do not present these opportunities to distance the setting so that students can develop a strong conceptual understanding of multiplicative thinking. So it is the responsibility of the teachers to provide these situations for students to stretch their thinking. The next 2 examples are going to be ways that I incorporate this in my classroom. So this is using notation to push thinking to that abstract idea. So drawing of arrays and notating student thinking with semi-formal equations can help them to see the decomposition of numbers. So to try and push student thinking of doubling a factor, I held a number talk in my classroom. If you're unfamiliar with number talks, they are short 10 to 15-minute questioning techniques for students to use mental math strategies only, and they're working on their communicating and thinking clearly. As a teacher, I listen to what they say and transfer their exact thinking to the board. This helps to promote discourse within the classroom and within interventions groups. So let's look at this progression where I asked them to solve 2 times 4, and then I presented them with 2 times 8, and then finally with 2 times 16. So with the 2 times 4, I had students tell me that they use skip counting, and they actually told me that they pictured the array in their head. So you can see under this 2 times 4, that's where I put the work for that equation. So you can see the skip counting and the array, and those last numbers that they said to themselves created that 8. Over to the right side of the screen, where I'm kind of circling with the mouse, you will see that I wanted to draw an array to show how that quantity of 8 was made. You can see those 2 groups of 4, and then there's, I dashed around each group to show them that they had 2 groups of 4 and that quantity all together made the 8. Next, I asked them, well, what would 2 times 8 be? So I wanted them to take their thinking from the previous equation and try and apply that to this second 2 times 8 equation. So students were right away able to tell me, well, 4 plus 4 makes 8. So then I did 4 4s. So in order to show how their thinking was, I had them do their skip counting because that's how the student solved it. And I wanted to show that 2 of those skip counting numbers actually made that 8. So if you look, you can see the 2 8s underneath the skip counting. Then I transferred it to equations. Well, 2 times 4 equals 8. Well, if I know 4 plus 4, that makes the 8 in the other equation. And then that 8, which was our answer in the 2 times 4, if I do 8 plus 8 or double that answer, I can see that the product of 16 was made by just doing 8 plus 8. Again, I connected it to the array and I showed another group of 2 times 4 to show that 2 groups of 2 times 4 is actually making that 16 quantity because each group equals 8. Lastly, I wanted to push their thinking to that abstract equation of the distributive property. So I asked them, well, if 2 groups of 4 makes 8 and 2 groups of 8 makes 16, what would 2 groups of 16 make? At this time, I took that array and I circled the entire thing, showing them that that was one group of 16. That array, if I put those two 8 arrays together, it makes a whole group of 16. Well, what would that be? Well, students told me that they needed 2 groups of 8 and another 2 groups of 8, and that would actually make the 2 groups of 16. So then I asked them to try and solve for that. You can see the blue writing underneath, the 2 times 16. Those are just showing how students were adding their numbers together and what they were telling me to get the correct answer of 32. So you can see how I was connecting the equations to that full array. Here is another example of how array support is important when you are notating equations. So in my number talks, you can see off to the side, there's lots of different answers that students provided. They provided 48, 24, 46, and 36. In these number talks, students will make mistakes because they are pushed to do mental math thinking only. And since these errors can still occur as students become more efficient with their abstract thinking, we need to help guide them on where they are making their mistakes. So teachers need to step back to that pictorial or concrete model so that students can identify where mistakes were made and they didn't pay regards to the accurate quantity. So mental calculation must come first, which is what these number talks promote, but then you want to push towards that pictorial and abstract to check their answers. In this case, the student thought 8 times 6 was actually 24. The array helped to showcase what he solved for and that they were not equal. So the use of pictorial and abstract helped to clarify their thinking. So one thing that was introduced in my classroom was a halving and doubling technique, which is seen in the middle of the picture. By that 8 times 6, a student halved the 8 to 4, and the 6, they doubled it to make 12, and they kept going to make it easier for them. Well, a student tried that technique. However, he halved both the numbers. So instead of saying 8 times 6, he said, well, I could just take 2 4 times 3. So he halved both the numbers, and then he thought he could take 2 of them. So from that, I went and drew the whole array for 8 times 6, so 8 rows of 6, and I showed him where his thinking was. Where were his 4 groups of 3? So I made sure to box those off, what he was thinking, and he was able to clearly see that the whole quantity of 8 times 6 was not accounted for, and there was some of the array that was left out. And he was therefore able to see that 24 didn't really make sense because the whole array was not circled or boxed off.
So supporting student learning when we're bridging the gap, we must use effective instructional techniques. Some of these instructional techniques, as you've heard, are questioning, discourse with wait time to promote student thinking, ongoing assessment, feedback, and micro-adjusting. In looking at this, we need to use, our questioning must be intentional so that it can promote student thinking. Often in instruction and intervention, it's us doing the math and showing students what to do. We need students to build this understanding by making these strong connections of their own. So therefore, our job is to guide this process with strong and effective questions that is going to promote these critical thinking aspects and push them towards advanced mathematical techniques. Questioning also needs to revolve around that overlap that we discussed earlier. When students are questioned and asked to compare representations and find similarities or differences, this builds flexibility to determine which works better for the context provided, as well as to zoom in on conceptual understanding of students. Discourse and wait time go hand in hand with the questioning. Students must have opportunities to talk about the mathematics as well as extra time to process. Think about how traditional instruction looks. Most of the time, it's the teacher doing the talking, and when the question's posed, students have fractions of a second before someone's called upon or a prompt is given towards the correct answer. The gift of wait time gives students an opportunity to think, process, and reflect so that they can draw from this prior knowledge before someone jumps in to guide their thought process. Students need these opportunities to discuss and reflect on the mathematics that's occurring during instruction. And an opportunity that we can use to create this is to show non-examples or representations with missing components and errors. Then students have a reason that they can explain their thinking. Finally, we must have ongoing formative assessment by constantly listening to how our students are solving problems and thinking about mathematics. This allows us to micro-adjust our lessons and provide instant feedback that helps students grow. I want you to think about this. Who does most of the talking in your classroom or your intervention groups? These instructional techniques we discussed are what helps us build strong connections, not only for our students, but gives us guidance as to how students are thinking mathematically so that we can meet them at where they are at.
So before we talked about how tools can become procedural, so here is another example of how this can happen and how we can integrate these instructional techniques into instruction to help students progress in their thinking. So here is a number line.
Jamie and Dina.
So as we work,
Jamie and Dina, I'm sorry to do this to you, just in the interest of time. We're just going to have you jump to the very last piece and know that folks will get a copy of your presentation. I'm going to.
Sure.
Okay.
Yep, moving through. So these were our learning intentions, and I want to give acknowledgement of where we received our information. So here's the acknowledgement slide that you can refer to. And we thank you for your time. If you have any questions, feel free to contact either one of us. Here are our emails listed below. Thank you.
thanks.
Sorry to do that to you. You had so much rich and specific examples to share. I just wanted to make sure that we honor the time that we have allocated to us. I know that some of you in the that are participants also work with secondary level students, and we will provide you with an example of what visual representations look like at the secondary level that Ken Davis from DPI has provided us. He's provided us with a short movie that demonstrates how you can build on some of the things that Dina and Jamie shared with us to build students' conceptual understanding. You'll also notice that in the webinar dashboard, there's a link to the materials that were shared, so you have a copy of not only this presentation, but the presentation that Dina and Jamie just shared, as well as a link to several resources that were referenced throughout the presentation that provide just general resources, teacher resources, student resources, some outcome studies around visual representations, as well as links to what Jamie and Dina shared as some helpful resources for discourse strategies. Finally, to conclude, I just want to connect what the presentations that we've done to date here. Our first webinar really talked about screening, moved into including motivational strategies. Last time we focused on intensely in-depth treatment of whole numbers and rational numbers. And today we work with visual representations. So I want us just to take a minute just to make some connections among those to see how all four of those concepts really relate. For instance, at the beginning, I shared that the visual representations that we want to select really are ones that help students to focus intensely on in-depth understanding of whole numbers and rational numbers and operations. So we have some time. We're going to stay on till about 10:15 to do some Q&A. We do want to thank you for attending. We have another webinar coming up in a month about systematic instructional planning. And again, we want to thank our featured presenters, Dina and Jamie, so much for all the time that they put into this presentation. One of the greatest gifts we can give somebody is feedback. So I'm going to ask that as a way to say thank you to them, that you take just a minute to complete the survey that you're going to get at the end when you log off of the webinar. It's just a 2-question survey of a takeaway and some feedback. That would be a really nice gift to give them. So we're going to leave this screen up here for our featured presenters, as well as the information to contact Sarah or me. And thank you again so much for attending today, and we look forward to continuing this conversation going forward.